want you to, think about everybody is not biased, but generate their own understanding or have their own belief of the size of the frac job, how high it is. Some people, and it varies in different basins. Some people think they're generating, only 100 feet frac height. Some people think they're generating, 1,000 feet. If you talk to different people, they have different answers, right? There are many different tools that are also giving us various different results. And out of that stimulated rock volume or frac heights, how much are actually effective, meaning that they are contributing to your production and become contributing to your revenue, right? So that's a two different concept and two different question, really, if you think about it, right? So the industry have been, study about shale or mud rock for many years, right? So there's the general background of the mud rock geology, which has been studied for much longer time. So that's the background, right? That's the background of everything that we do. You have the general geologist in there. The SRV is something that's in recent about, from the shale boom 2009-ish, it's 10, 15 years. So it's the SRV is something that is one-time thing, right? It's about the fracture that you generate, right? And it's not necessarily draining or contributing to a production. For industry, that's very important, right? You have to be able to stimulate that rock for it to flow. However, we are, as in general, oil gas industry, we are rewarded not by generating the world's largest frac, right? And we don't actually want to do that, right? Because there are environmental implications of that. So what we wanted to do is to generate effective drainage rock volume, right? And we wanted this delta to be as small as possible to minimize environmental impact, right? You have all those microseismic or fiber optic, those events that can telling you may be the SRV maybe 1,000 feet, or sometimes even I've heard numbers 2,000 feet, still hear response. But are you draining from that, right? The drainage is really what we care, and also it is a concept, or it's that the drainage rock volume would really change through time. So it requires even more accurate and also a time-lapse monitoring through time. Because if you think about it, geology don't change with time. SRV, once you frac, boom, one-time thing, done. That's your stimulated rock volume. Your drainage is the only thing that would change with time, and that has the closest tie to your dollar sign, essentially, about your financial performance of the well. And also, that's something that can be adjusted, that can be engineered. I mean, geology, you cannot engineer it. SRV, of course, that's something engineerable, as well as the DRV. And DRV can be have element of being engineerable, not just one-time thing, but also through reservoir management. And really, that concept is less than 5 years old. That's something that's we are really just starting to understand. So that will be what the concept of drainage rock volume, whether it's oil or it's gas or it's water, is what the focus of our discussion today. So, okay, so let's talk about oil fingerprinting in general, oil geochemical fingerprinting. It can be anything. It can be in a gas, and I'll talk about it in a little bit about the gas as well as the water fingerprinting. But in general, the geochemical fingerprinting concept is the process of determining where a sample of oil originated from. Essentially, that is originally a concept from actually the environmental side because of the oil spill. Like in the ocean, oil spill, they find the oil and they track that back to who is responsible for that oil spill, right? So it's the same concept because the oil, you think about it, routinely we resolve over 2,000 compound in a drop of oil. 1 milliliter of oil, over 2,000 compound. Think about it. There's tremendous amount of information in there. So here is one of the tools called multidimensional gas chromatography, and each of the peak, if you look at it, is a different compound, and it's like a Google map. You can zoom in, and there are more compound in there. So the oil is a very information rich. It has a tremendous amount of information that are carried by those hydrocarbons. And if you think about it, those hydrocarbons come from organic origin. It's different organic origin, or during its migration, like when it's migrated from the source rock, let's say from Wolfcamp to your third bone, it's passing through a lot of kerogen, clay that have different affinity for certain type of compounds, such as aromatics versus others that are, more of a straight chain, and also different mineralogy, different depositional environment. Those are all the reasons that could causing those so-called fingerprint to be different, or chemical compound information to be different between your, upper Wolfcamp A, lower Wolfcamp A, third bone, lower third bone sand and carbonate, right? So that's what gives those unique fingerprints in different of your geological formations. And that's the basis for geochemical fingerprinting in general. So the concept of using geochemical information to understand where that hydrocarbon came from is that we call it production allocation. Essentially allocates the oil that you produce back to which formation it's coming from. It's nothing new for a conventional reservoir. That concept started from the 70s and 80s, and you can, I won't read that through, but there's a lot of literatures and history of that. It started by a lot of pioneers, geochemists at Chevron. It was originally a proprietary technology at Chevron, and then it was used in lawsuits, and then it need to publish on that, so it become publicly available. And then originally it's used in, as I mentioned, in a conventional reservoir when you have commingled production or reservoir compartmentalization, different compartmentalization of the reservoir to understand the commingled production from formation A, B, C, how much is from what formation, right? And then it become a standard tool for doing production allocation. Actually, Norwegian government do recognize this as a tool for royalty calculation for different formations. So, Shell, Conoco, myself, I worked at ConocoPhillips before I resigned to start my own company. So it become a standard tool in conventional reservoir to do production allocation, to understand where that hydrocarbon is produced from. However, the unconventional application is really just recent, and we will talk in the next slide why what's the difficulty that are preventing this technology being widely used in the unconventional reservoir, and what's the solution now on the market to be able to resolve that. So I got questioned that, well, this sounds like a black box, like oil, and then I give you either, a rock from different formations or oil produced from each formation, then a commingled oil, you tell me the percentage of that. And I put this together to explain this is not a black box. Geochemistry is a discipline been there for 50 plus years, right? I can pinpoint to you what are the compounds that are differentiating between different formations, and which is the basis of why we're saying certain percentages coming from each of the formation. So I want to draw eyes to three of the compounds just for illustration. This is actually a Permian case. This is the base of the Serpong sand, and then upper Wolfcamp A, lower Wolfcamp A. In this case, the operator landed their well between, in Wolfcamp A, and in the hope that it would drain all those three. And when we look at when we say geochemical fingerprint, what we really mean is the relative abundance between different compounds. Because no matter where that oil is coming from, whether it's from Permian, it's from Eagle Ford, it's from North Sea, it's from Middle East, it's going to include roughly similar that 2,000 plus compound. So its composition, what it includes in the oil, is fairly consistent. However, the difference are in the relative abundance between different compounds. So that's exactly what we're talking about with geochemical fingerprint. So I want to draw eyes to this pair of compound ratio, biphenyl versus 2-methylnaphthalene. In the lower Serpong sand, that ratio is a 1. As you get to the Wolfcamp A upper, it's 0.5. And the lower part of the Wolfcamp A is 0.2. Okay, it's reducing as it gets deeper. When you get the produced oil, we measure it again, and it comes back as 3.85. So essentially, all we're doing, there's really nothing fancy that goes into the production allocation model itself. You're essentially mixing a 1.5 and 0.2 to make a 0.385. And this X, Y, and Z is the mixing ratio. And that comes back, 10%, 35%, 55%. And obviously, you see there's not one equation, right? You're not, otherwise, if you're using one pair of ratio, you're running into the non-uniqueness problem, right? So that becomes the beauty, like why you need a lot of compound, hundreds of them, sometimes thousands of that to constrain a solution. It's like running a reservoir model, history matching it, right? The more constrained flowing bottom hole pressure, water rate, gas rate, oil rate, the better you have, then that reduce your uncertainty in that history matching process to come up with the right number for the number that you want to know. In this case, is the mixing ratio. And in this case, I want to draw your eyes to three of the compounds where they are in a chromatogram. So they are between, I know it's very small, so apologize for that. It's between normal alkane 13 and 14. If you use a low resolution, the traditional GC, which is a one-dimensional GC that gives you 100 compound or less resolution, that information would have buried between those small peaks. So that is the one challenge that we have with running production allocation in unconventional reservoir, is that the old low resolution tool, analytical tool, is not be able to capture that fine granularity difference that we needed for unconventional reservoir, right? For conventional reservoir, we're happy to just tell the difference between Wolfcamp A, my Avalon, my Woodford, my Barnett, right? That's all about those salt rock. That's all what geochem is about. So the tool haven't really changed from that 70s, 80s. That's still the same tool, which is fine. If you are only interested in telling, let's say Gulf of Mexico, you have ABC reservoir, that's it, then the lower resolution is fine. However, for unconventional reservoir, it's different, right? We wanted to see every 10 or 15 feet how far my fracture goes, because every feet matters, and that all matters in terms of how to place my wells. So that leads to the discussion of what are the things that are different in the unconventional reservoir. Why unconventional reservoir is so challenging, right, to do the production location. So here is actually I gave this talk, APG or talk about this. Essentially, for conventional reservoir, it's an easy apple-to-apple comparison. You let's say in Permian Central Basin platform, you have Fossilman, you have your Wichita-Albany, and different of those reservoir that will flow naturally. And you have a old well that's just completed in the Fossilman. You collect the oil from that well. You have a well that just completed in a Clear Fork. You collect the oil from it, and another formation, Wichita-Albany, whatever. And then you have 3 oils. And then you have your commingled oil. So that's all you do. It's an oil to oil production allocation. That's the easy part. Most of geochemistry group can do that. However, in the unconventional reservoir, you can no longer establish your baseline oil in that way because, let's say Wolfcamp, without fracking it, it would not flow naturally. So you cannot just get an oil sample from that. You need to frack it. However, once you frack it, it's not a 100% Wolfcamp anymore, right? So we have to use rock and extract hydrocarbon from it. So, and how to properly extract only the mobile hydrocarbon, because we know the recovery factor is only about 10% or less, how to extract the relevant part of it. That's another difficulty. So I think the key difficulties that are moving, transferring the knowledge from production allocation in the conventional reservoir to the unconventional reservoir is twofold primarily. The first is how to establish the baseline using rock sample instead of oil sample. The second one is to having much higher resolution to be able to tell the fine granularity difference, right? So the tools to do that, you will need to have a higher resolution chemistry so that I always made the analogy, this is similar to go from handheld microscope to the SEM, so that you are able scattered electron microscope that gives you much higher resolution under the for the rock, right? A 2 piece of rock, you may not see the difference, especially for shale under regular microscope. But if you put it under the right resolution, then you definitely see the difference. So you need to have the resolution that are enough to capture that, and also have the extraction method to properly establish the end member for it. So I won't elaborate on that. There's, we could spend many hours on that. But suffice to say, unconventional reservoir production allocation have its own challenge. Using the same tool from the 70s to 80s, it's just not going to solve that problem for you. So let's talk a little bit about gas and water before we have a break. So I understand this is, a very water-focused audience, and I got this question very often too. We've done this successfully with oil. Can we also do that? I also wanted to know where my gas and water coming from, right? And there's some even more challenges with gas and water. And I'll tell you why is that on a very high level. So the biggest problem with gas is there are 2 things. The first one is the data richness, right? We talked about oil, there are thousands of compounds to help you constrain, right? Because I need to find compounds that are differential between each of the benches. A lot of that compound are just not differential, right? So we need to, in the beginning, start with a big pool of data. The gas, you have carbon number from 1, 2, 3, 4, 5. It won't start to have isomer until you have 4 carbon number, right? There's no other way to connect 1 carbon, another carbon, a third carbon, until you have a 4th one, whether to connect straight or connect it in the middle, right? So, and until carbon for the gas, you have till about C5. So you have no isomer for C1, no isomer for C2, no isomer for C3, 2 isomer for C4, 3 isomer for 5. That's all together 10 compounds, along with some double bonds. We're talking about a handful of compounds, right? And they have to be each very unique, which is a very challenging thing, right? You need to start with a big enough a pool, and so that you can find some compound that are differential. Another challenge is more fundamental, which is the first gas that just came out versus the later gas are actually different. There are studies on that because there are desorptions going on. What's the isotope signatures in a free mud gas versus putting it next to collect the headspace gas for 12 hours, 24 hours, 184 hours are very different, right? So what is a true end member, right? That's another difficulty. Like it's not a what's in a free gas versus desorbed, which is going to happen during your production. How to properly establish your end member, that's another challenge. So yeah, but I've done that. There paper that I published in 2017. If you have interest, that also shows some gas data. So far, the industry, the oil, it can be done quantitatively down to about 10 feet resolution. The gas and water, we are still at a stage of semi-quantitative or qualitative understanding. So here's about water. So the deal with water is even more complicated. I think water is the most complicated out of the three phase. Why? Because you're not solving one problem. For me, for oil, I'm solving one problem. The oil coming from different zone, right? That's coming from different formation is only the difference. That's the only source for my oil. For water, it's different because you inject a large amount of water. That's source number one, problem number one, right? Number two, you have different formation brine. That's question number two. And question number three, water rock interaction. The water that you inject would work with your rock and come up with different cation anions. So that's a very complicated problem to start with. Sample and there are other issues which I think is more secondary. Sample preservation. You need to preserve the cation and anions differently. Otherwise, CO2 escape from your water, change the pH, and that's no longer good data for cation anion. You can try using stable isotope, but which is the case that I show here, strontium, boron, chlorine isotope, but they need to have enough distinction. The linked dots represent for each formation the extracted water, and in the box is produced. You see, they're still very hard to constrain quantitatively. So it has a wide range. So and each of the isotope are very expensive to do. You need to have a variety of those stable isotope that have enough concentration in your water to allow that. And let alone the problem of establishing a baseline, how to extract water from the rock to establish your baseline. So yeah, with that, I will open that for a short break. If any of you have any questions and or comment.
Okay, we just got a question from Andres. He asked, could there be filtration or chromatographic separation in the reservoir, and what is produced is not the same as what is left behind, and how would this affect the rock fluid interactions?
Yeah, that's a very good question. So in terms of oil, there's less so. There's less so. The water, there's definitely and the gas, the desorption, and for the oil phase, there is less of such a chromatography effect. That's actually a valid concern. We did a lot of study on that, and so that is why a proper extraction method to establish the baseline is very important. So traditionally, either this one or the one before. Yeah, let's look at this one. Traditionally, if you give a piece of rock to any geochemist and say, I want to know what's the oil composition is like, We would do what's called solvent extraction. So usually either a CS2 or dichloromethane to extract everything out. That include mobile oil, bitumen, sometimes even kerosene in it, all the organic matters, right? So, and only a small fraction would produce. So that's actually the topic, in 2019 in APG, I was invited to give this talk with Harris Kanders at Marathon that we did this study and we have other traditional geochemistry methodology as a comparison. So the solvent extraction method is going to just as similar effect as you mentioned. It got everything out, and only a small fraction are relevant to production. So properly established baseline using extracted, whether it's water or oil from the rock, is absolutely the critical step. And that's why that's one of the key reasons that motivate me to start my own company, because I was frustrated with the data that I got because it just have a lot of irrelevant information, and I have to go through a lot of data to find the percentage that are relevant to production. So yeah, you're exactly right. I mean, how to properly establish the baseline. That's the key here is to have the right extraction method there to help you establish that. And the physical extraction that we use, that I think currently are that are working on. There's over 1,300 wells there that we're under monitoring now, is actually all using the physical extraction, which is not involving any solvent, right? Yeah. Anything else before I run to the next case studies? All right. So if not, we will move on to the next page, which is a couple of case studies. So before we start the case studies, let's spend a minute on the two sources of geochemical data and how we can use that for the reservoir monitoring and the reservoir characterization. So there are two sources of geochemistry data. The first one is oil extracted from the rock. The second one is directly from produced oil, right? So from the first source of data, which is the oil extracted from the rock, we developed tools, algorithms that are actually by data mining the information we have to understand reservoir quality, essentially reservoir permeability, and also oil in place. So the reason the geochemistry data can tell us about reservoir permeability is because of the extraction method. From the time that the rock, whether it's cutting or core, pulled from the subsurface to the surface to the lab, there's inevitably some loss. And by observing, data mining what's lost versus what's still in there, we can get better understanding of the rock permeability, because everything else equal, the more permeable the rock is, then the more loss you have. And we come up with algorithm to understand that. And also the oil in place index, which is, you load the same amount of rock and look at how much oil you're able to extract, so that you get an idea of, where my richest zone, and also where my highest perm zone, so that you can optimize your landing for that. And what's more interesting is that once you do the production allocation to understand, okay, my well one is producing 30% from upper C, lower C, and majority of that from lower C, I can come back and see, okay, what is about formation C, that is the lower part of formation C, that is make it become the key contributor to my production. Like what make it so good, right? So that I can guide my future drilling. So yeah, so that's why, you know, there's not just the reservoir monitoring part of it using geochemistry, which we have been talked about, but there's also an element of reservoir characterization. There's also an element that I wanted to mention about water saturation index, because this is a water audience, that we also have, you know, come up with some indices that related to water production, and to use your chemistry knowledge. We know that, okay, there are certain compound like naphthalenes or benzene, they're 10 times higher water solubility than your, say, normal alkane. And if you find very low concentration of those high water soluble compound, that indicating that you are encountering a very high water saturation zone, right? Other things equal. Anyway, so I think we're just at the beginning of leveraging our chemistry knowledge to understand the reservoir, to help understand the reservoir. It's really, it's not a new data set for the industry, but for the production stage, it is absolutely a very young data set. And the second piece is the reservoir monitoring, right? You have the, you establish your baseline vertically. This is actually a Midland Basin case that we published with Diamondback last year. So this is about, you know, all the way from Clear Fork to the Wolfcamp B, and so yeah, the entire interval of it, we monitored several wells, and here we show 4 of that, well 1, 2, 3, and 4. And this one we call it fitted drainage frac height curve. The horizontal represent percentage of contribution, production contribution from each of the formation, so that you're able to get idea of through time how much zone are contributing, how much production you're getting from each of the zone. I want to point out a couple of things. In this case, well 2, which is landed at the top of the formation D, as you can see, still majority of its production are coming from the zone above it. So that means that, okay, this is probably not a very ideal landing zone, because it's overlap noticeably with the drainage of well that's landed above. So, you know, landing target adjusted accordingly. So, and the second part here is that the well 3 and the well 4 have a noticeable overlay in their drainage, which is not necessarily a bad thing, but there's a very interesting interaction between those two. So in the beginning, well 3 was not online. The well 4 was able to drain into the formation E. However, after the upper well was put online, that contribution immediately disappeared. So that comes with the question of, you know, exactly touching the point we talked about, SRV versus DRV, right? Yes, your model may show, or other data, physics-based data may show well 4 frac go all the way to your formation E. However, how much contribution you're getting from that formation E, and for how long, right? If it's only contributing a few percent for a few weeks, then it matters much less than if it's lasts for years and contributing, you know, significantly, right? So this really give you a quantitative time-lapse data to allow you to make very accurate decision making, right? As we talked about data-driven decision making, that's exactly that, right? Providing information for that, and you know, there are different applications. This is just the data set, and it can solve many problems depending on how you use it, right? You could use it for different completion design. We have people that using it for different, you know, from gel to slick water, to look at, you know, are you draining different rock volume? Are you using a different fluid system? Or if you use a different EOR, like gas injections or chemical EOR, are you still reaching out, touching the same rock volume, or you're actually reaching out to additional rock volume, right? We do a lot of gas injection. Are you really just jack up the pressure back up to the single phase? You're still producing from the same rock volume, or you're actually touching additional rock volume, right? So the application is endless, and the innovation part is really driven by you guys to come up with, okay, look, this is just information source. How use it is not limited, right? It's on the design of the experiment. So here is the vertical profile in terms of reservoir quality index and oil in place. And this is the vertical profile of the geochemical fingerprints, a pair of the ratios actually to it here. If you look at it, they are different as it goes deeper, right? And when you get oil, you measure it, let's say that same ratio is at 0.1, then you come here and say, okay, my formation E and F are my key contributing zone, right? That's the foundation of production allocation, is to match the information you collected from the rock to the information from the oil and match that. And this is just plotting in a different way. Both X and Y axis are two different ratios. Just for illustration, because actual production allocation, there are hundreds of ratios going into a computer model to do it, right? This is just for illustration. Color coded by different zone, you have A, B, C, D, and there are different zones in there, and so they're very unique. You see they're color coded differently for different formation. And then once you get the oil, so that's the thin cross, which is the oil. And you have the well 3 oil, thin cross here, and well 4, which is the pink. And you see the well 3 overlay best with the purple, which is the formation E. That's how we know that it is a well, it is a formation E produced, or formation E is its key contributor. And also well 4 overlay with the pink. And we also, okay, so so this is the cross plot of the oil only, because in a lot of times, sometimes you don't have baseline, right? You don't have a cutting or core to work with. However, the information that are in your produced fluid does not discount or change at all if you have a baseline or not, right? So the oil itself, or information in the oil, or in any other fluid type, would carry a lot of information. In this case, well 1 and well 2 are noticeably separating each other, right? You don't need to try very hard to tell that those are from two different wells, meaning that their drainage are different. And for the well 2, through time, there is a very interesting time-lapse change to it, which if you want to, they're in the paper if you want to know more about it, between the interaction between well 1 and 2. Yeah, so this is the plot, stack plot for the production allocation, so that okay, this is about well 2, which is this guy here. The lighter, I don't know, this is a green. In the beginning, there is 50% C, which is increasing through time in the first weeks of production before it stabilizes, right? And once it stabilizes, you see majority of its contribution is coming from the zone above it, right? And also notice there's a little bit of green that's in the formation E. And the model is showing that, okay, you may have other seismic or whatever data that you have that indicated frac downward into the E. And that's true. We do pick up some production from there, but it's a very small fraction, right? It's been on average 5%. Yeah, so this is the production allocation of the well that are in the formation E. And this is what I mentioned before well 3 was put online. There's a little bit of green, which is the E formation here. And the moment the upper well put online, you stop seeing that. So yeah, so when we drilling, so close now, there inevitably those well are in some type of talking, right? Pressure, they respond to pressure. However, having pressure communication does not necessarily translate into drainage fluid communication, right? Even if it does, how much, right? So that's the key question we are answering from using the fluid data. That's really the bottom line. So in this case, we actually looked at the parent well frac kit, getting a frac kit. In this case, we have a parent well, which is we collect the oil fingerprint. Unfortunately, I wasn't get permission to show the actual production location of it, but we do have that parent well monitored before the infill drilling happened, and the signature is in the blue. It's more of a dominated by single zone production. However, the well was shutting and for the infill drilling to happen, right? The moment that the well put back online again, after that infill drilling, it moved to the orange. There's a significant change and started to see much more external contribution after the infill drilling activity. So we'll be able to give percentage of how much that impact is. And then, but after about 2 to 4 months, depending on different wells, it all moved back to the green area, which is, pretty much back to the blue. So that means, the frac kit, okay, how much impact do you have and for how long, right? So this is what the fluid can provide an answer on. So I think we are getting to our last two slides so this one is on the recovery factor calculation, right? So understand, which is a very key factor to understand how much inventory you have, right? A lot of places are, I hear operators saying, well, they're running out of inventory, or what's the, get better get better oriented on where to drill their infill, right? So this can definitely help that as well. So what you can do is that you can get the EOR from your existing well, from your reservoir engineer, right? To get an idea of how much oil recovered from that well over a 10 years period of time, let's say. And then you can times the production allocation results, 13%, 25%, all that. And then divided that by your original oil in place, right? So that you can get an idea of what's the recovery factor of each of the zone, And when you look at those numbers, they're 6%, 10%, 12%, 2 and 0.4%. We know unconventional reservoir regular recovery factor is, less than 10%. And this is telling you it's not a uniform 10%. Some of the formations are getting close to conventional reservoir, while some are even lower than we had imagined. So how to, that would give you implication this well is not draining your formation F very well, not the lower part of your E. And you can also look at the reservoir characterization indices to look at how much oil there is in the formation F. Maybe there's a lot of oil. Then you could think of, okay, I need an infill well there. I could update my reserve, and there's more oil in there that haven't been drained. So that's just different ways to using that data, and how to integrate the static characterization with the dynamic production allocation, so that it's not just a monitoring tool, but it's also guiding your future drilling and the future reservoir management. And with that, I think, a quick comparison between geochemistry-based method to monitoring the fluid, to monitoring the reservoir versus others, right? I wanted to emphasize that this one is think about it. This is the only tool that have the possibility to be applied to provide value for every of your well, because you cannot install fiber on every well. You cannot dose tracer for every well. You cannot do fiber optics for microseismic area of your well, it's going to cause too much interruption to your production. But I really encourage all of you to start collecting your fluid, whether it's water, whether it's gas, whether it's oil. It's really include tremendous amount of information in there. The industry have been focusing so much on collecting physics-based data. You have pressure data, you have water rate, gas rate, oil rates, and acoustic and temperature drop. There's limited amount of physics-based data, and the chemistry just providing such a data-rich and cost-effective way to collect information about the subsurface. Yeah, with that, I will open that for questions.
Okay, Faye, we had another question from Andres. He said, how would geochemical tracing compare with normal oil, gas, and water tracers?
So, okay, so first, this is not dosed. So this is almost like a natural tracer that are inherently in your oil already, right? The chemical tracers is well, first is dosed, and depending on it's a more complicated system to interpret with, right? How the tracer are being dosed to and interact with the formation and come out. So it's not I think the chemical tracers are good for understanding lateral different stages. That's good for that, and for during the early stage of production, because after months you started to see those numbers drop to sub ppb level, and as a chemist, I question how reliable that data anymore. So it's I think it's answering different questions. It's more on the lateral different stages. And again, look, there's thousands of compounds that are naturally occurring in your oil. For tracers to dose, let's say you have 50 stages, you need to have different varieties to allow that to happen. So, and it's yeah, and it involved just as the water production issue, there's more process involved, right? That tracer needs to first get into the formation and then come out, and we need to understand how that happened, which I don't think that's completely fully understand and just yet. It's a more it's just like the water production location, how I've done a lot of water monitoring as well. A lot of time by a few months, you're already 90% above formation brine, right? Using the volumetric to look at how much water have already been cleaned, wellbore being cleaned is really a bad way to do that, right? So there's still a lot of unknown how that tracer goes in and comes out. But on the lateral perspective, I would say geology changed much faster vertically than laterally. So I definitely think the tracer on the lateral parts do have applications that I think are useful, but there's still some question marks that I think need to be addressed.
Okay, thank you. We also had a question from Josh. Based on your own SW data, do you find that the water cuts observed in unconventional plays are reasonable? And how does your data compare with log core SW interpretations?
Yes. So the water, let's show this one. So this is the water saturation index. What's go behind that is the water solubility or fraction of water. Essential indicator for water solubility of your benzene, toluene, naphthalene, xylene versus your normal alkane, right? And naphthalene, phenanthrene over normal alkane. So there are certain compounds that are having much higher water solubility than the normal alkane. Now, if you're using, because majority of the rock that we work with are cuttings, because which stone, the industry in general are getting less and less core. So the cuttings, because of the water washing of the cuttings, that may bring some quite a bit of uncertainty to that, especially, the DPC drill bit now pulverized the cutting, which means a large surface area, causing that uncertainty. For core, so those are always indices, meaning that it's showing a trend. I cannot provide an absolute value. I cannot tell you, your rock is 500 nanodarcy or 1 million microdarcy. It's not intend to do that. It's intend to be in a relative quantitative way to do that. It's the reason that it's quantitative, or we call index, is because this is all related to the sample preservation. For older cores sitting there for 10 years, all that will have less oils remain, so that oil in place index will reduce, right? For newer core, it will all have more oil left in there, so have more. And also for older core, it's all going to have more light and loss, translating into higher reservoir quality index. However, that trend would still remain as long as that sample is preserved in the same way. The higher perm still have more loss than the ones that are lower perm. So just to answer your question, I think in general for core sample, there's if we have enough compound recovered in your robust compound recovered from the oil extracted from the rock, in the cases we see, they're reasonable agreement, and they're not everyone is in agreement, which I put a question mark, which one is correct. There's still debating room to that. The reason we haven't included the water saturation index in the standard deliverable, that the reservoir quality index, oil in place index, are using hundreds of compound altogether, right? So it's altogether there are thousands in most of the case. It's very robust. It's a very information data rich data set to come out. So we have a lot of buffer room if one ratio is off or one compound is off. The water saturation index are relying on a handful of compounds, right? Between 10 to 20 compound. And if it's not uncommon to have half of that the peaks is too small, that introduce significant error to it, right? It's all about a statistically meaningful number of information so that it can buffer out each other in case there's any, we know there will be bad data. So that's why you need to have a lot of data to work with. And the water saturation, unfortunately, is relying on a smaller data sets, so it has higher uncertainty. But in the core cases, we see a lot of cases that are agreeing, and there in some cases not agreeing, but I think there's reason behind that.
Okay, thank you so much. We also had a question from Drew. He said, have you been able to explore the horizontal component of reservoir characterization, adding a spatial element to the vertical profiles for a 3D analysis, or is lateral variability too low to use cuttings and core from horizontal wells?
Yeah, thank you. This is a great question. So let's actually talk about it. It's a very interesting. That's our focus now, actually. One of the focus now is the lateral resolution, because people, drilling longer laterals, and we're able to get our hands for, there's several pilot we're running that we're able to get our hands on lateral cuttings. And we did the reservoir characterization, and it does show variations. And this is the collaboration with Completion Group, that they're using this information to optimize their lateral completion design. So where they have high reservoir quality, and they would put, tighter cluster spacing, and where it needs extra help, lower perm, then they have other designs. So yeah, they are of that. Geology change much faster vertically than it change laterally. It's a given. However, every few hundred feet, we definitely see geochemical change. We say that you can use that same baseline in a radius distance about 3 to 5 miles. In some cases, geology change faster, much faster laterally. There are some cases we've seen even 2 miles, you see noticeable change, while in some other cases, longer, you see less changes. So on the rim of the basin versus center of it, there are different speed of how geology changes. We do a lot of work in Eagle Ford, go down dip, up dip versus parallel to the dip. It's very different. You can go much longer if you go parallel to the maturity versus go up dip and down dip. So yes, laterally it is. We have use the lateral information to understand lateral well communication, and the lateral XF, how much XF overlap. Because we can understand not HF, more of a drainage frac height very well, down to 10 to 15 feet resolution, very confidently. Laterally, we cannot do that. And but quantitatively, we can understand if we have 1, 2, 3, we can see between 1 and 2, they're more talking versus 2 and 3. So there's a qualitative number that you can come up with using the lateral information. And you don't necessarily have to have lateral cuttings for it. We can just use the oils, look at, is this one well and 2 are more similar? I mean, more XF overlay versus 2 and 3.
Oh, okay. Mindy has stepped out for a minute. The next question is, are there ways that your hydrocarbon fingerprinting method, which adds dimensionality to standard chromatographs, could be applied to some components of water analysis?
That's an interesting one. I think that's a possibility. I mean, if there, we actually done looking at the VOCs that are dissolved in the water using this and getting quite good information on there. We are also actually applying this in medical materials. My husband and I founded this company together. He's a biochemist, he has a PhD in biochemistry and worked in medical centers. So he has that element of it. And we actually get approached last year during the pandemic and saying, they want exhale breath analysis for COVID-19 detection, because the lung exchange blood with breath, and if it actually proved for FDA for early stage lung cancer detection. And our setup is actually, we need to do very little modification to come on that. Actually, we successfully did breath analysis just actually in early last month, and we have profiled all RevelCam employees' breath now. And so it's definitely not limited to just oil. That increasing resolution of compound resolution, in particular the VOCs, volatile organic compound, whether it's in your breath it can be used for other biological materials or environmental monitoring, and it's used for food industry, for wine, headspace wine, for essential oil. Definitely, I'm very open for if you have any idea or thinking, if they're compound in the water, we'll have to discuss, how to prep the sample to be able to analyze that. But I'm absolutely open for discussion. Yeah, and I have my contact information in the last page. Feel free to, email, call. Yeah, and I also have, any question that's, feel free to give me a shout.
Thank you so much, Faye. We also had a question from Dr. Nana. Can the fingerprinting technique be used to identify the source of produced water?
Yeah, so that's one of the things we are at the beginning of RevelChem, because I've done all those three, right? And Josh probably knows this. Josh worked with me on this from many years ago. The different route to go. There's the oil, there's the gas, there's water, and I think the oil, because of the information richness. So that's the first one that I jumped onto. I know it's going to provide enough information to constrain when you have, for example, the case study we showed have over 200 end members, so have enough constraint to constrain that. The water is, it's a tricky one to work with because of the, you're not solving one problem. You have the injected water, you have water from different formation, water rock interaction. There's just a lot of question to answer first. You first need to find a part of the water that are coming from the formation, and then need to find enough information to distinct each of your formation. Even, not even 10, 15 feet resolution. Let's say 500 feet resolution, right? That's not even a trivial work to start with, and half of the time I'm dealing with water, I'm dealing with bad data, how to put the cation, anion, preserve properly. Oil is like, it's already biomarker, so it's very robust. It's already very well, it's cooked, and you cannot mess up with the oil. I have oil that's 20 plus years old in the fridge, still fine, and they're sitting fine on a subsurface for millions plus years, so they're fine. The water just needs a lot of attention to keep the information valid, quality data. Otherwise, the stable isotope, I think, is your best friend, but it's a very sort of expensive, and not many company provide that. And also, even that, you have less than a handful of stable isotope to select from. Each of that need to have enough concentration. You need to have enough of, strontium, bromide, boron in your water to allow that isotope analysis in your core sample as well. So that, and they need to show distinction between each of your end member. So I think it's water is definitely something that's very important, and that needs more research. I think that's what need more leverage between the universities, research institute, and the industry to collaborate on, so that, because it's still at an early stage. I think it's probably, as 10 years ago, where the oil fingerprinting is at. I think it's that stage that needs more research attention to have that early time to get that those fundamental questions answered first.
Okay, thank you so much. We had another question from Drew. He said he was curious about the use of HRGC for lateral optimization and geosteering type applications.
Yes. So the lateral optimization is you get the same reservoir characterization and oil in place, but it's just laterally, so that you will be able to see, okay, where you have higher reservoir quality zone, where you have, a higher saturation, so that in some of the cases, I'm surprised how much lateral variation we see. The challenge is that we don't always get those samples, right? It's because for oil fingerprinting, we need water-based mud cuttings or core. Core doesn't matter, oil-based or water-based doesn't matter. Not many, most of the companies is water-based vertical and then switch to oil-based mud for the lateral. So that's become a challenge. But once you have that cutting, you can do the same thing. Reservoir characterization laterally, so that you can optimize your lateral completion design.
Okay, thank you so much. And our last question is from Andres, and he thanked you for all of your insights thus far. He said, what is the extraction process for field samples? Is that done downhole or is it at the surface? And in any case, in unconventionals, a lot of fluid is injected. So when is the sample considered pure? Would too much production time affect composition on the fluids?
Yeah, and just, yeah, thank you for your question and your nice words. Yeah, it's surface collected samples, very simple. It's cuttings are collected by the mud logger at the surface to establish the baseline, because you know exact sampling depths of that sample, so you don't have the issue of, you know, mixing up your samples. You know the depth. That's the ground truth. That sample is coming from this depth interval. You know, mud logger collecting, there's usually a plus minus 10 feet, which is fine. So we know exactly where that sample is coming from. So we extract oil from that. So we know exactly what oil fingerprint is like at that depth. And unconventional, you don't inject oil in there, right? You won't mess up with the oil. You can mess up with the water. You know, oil is actually blessed in terms of you don't get interruption from external interruption because you don't inject oil in it. And also the only source is coming from different formation, and also the richness of information. So I think that's why the oil phase is the first getting figured out, right? And the gas and water is probably going to follow. The timing of that, depending on how much effort, how much, you know, research attention that it can get. Yeah, would too much production time affect composition? It would change composition of the fluid before C12. It won't impact the range that we run production allocation on. So the range of compounds that we use for production allocation is intentionally selected to avoid any impact from PBT effect, you know, changing phase and all that. We use that for other purposes, for reservoir management and other information, but specifically for production allocation, we don't use the light ends that could be impacted by phase behavior. We collect sample at the separator, room temperature, pressure, that oil, no pressure. Yes, Andrews, not no oil-based mud drilling has been. So we don't use oil-based mud cuttings. Oil-based mud core, rotary, whole core is fine. The problem with oil-based mud cuttings is not the oil-based mud itself per se, because the oil-based, you know, it's diesel, it's a very specific range. We could digitally subtract that. It's not the problem. The problem is there are two things. The first is circulating of mud. So you have, you know, you drill through first bone and there oil getting into the mud system and recycle. And so you get a lot of produced oil that mixed into the mud system, that made the mud system. We've sampled oil-based mud, you know, during drilling, after drilling, it already looked just like produced oil at the end of, you know, during that drilling. The second thing is the DPC drill bit. Like now everybody's drilling as fast as possible. So if you look at the size of the cuttings from those oil-based mud DPC drill bit, essentially it's powder. So they have very large surface area. So those mud invasion just happening very fast. So correct. No oil-based mud cuttings. So we've done actually quite a bit of oil-based mud cuttings for the indices, for the reservoir characterization indices. They're still fine. They're still working reasonably well, even though we don't want to deal with that. I mean, we still need to use solvent to wash out the mud. It's, you know, but the indices, because it's used hundreds and thousands of ratios, so you have a lot of buffer. So it's still pretty robust. However, when you're talking about individual compound peaks, a lot of them could get impacted. So production allocation, oil-based mud cutting is still a no-go in my opinion. No problem.
Okay, and Faye, it looks like that is our last question. Is there anyone else that wanted to speak verbally to offer any other questions for Faye? Okay, and Josh, did you have anything else that you wanted to add here at the end of our lecture?
No, ma'am. I appreciate everyone's time today. It was really interesting. Thank you.
Okay, wonderful. Thank you. Dr. Nana, would you like to close this out?
Oh, yes. First of all, thank you, Dr. Liu, for an excellent presentation. And thanks everyone for joining us. This lecture series is sponsored by Chevron. We are very appreciative of their continuous support. I would also like to thank Pioneer Natural Resources for giving Josh the time, to invest as the subcommittee chair for the lecture series. We're also getting support from B3 Insights, the University of Texas Permian Basin College of Engineering have been very supportive. Most importantly, I would like to thank Mindy and her staff for coordinating this effort. She has been doing an excellent job, so I would like to thank everyone for participating. Stay tuned for the next lecture series that the announcement will be coming up shortly in the next few weeks. Thank you.
Thank you, Dr. Nana, and thank you, Josh, for the invitation. Thank you, Mindy, for helping me setting up the talk. Really appreciate it. I had a great audience, and I'm very excited for this opportunity. Thank you.
Thanks.
Thank you so much.
Bye.
Bye.